Hello, everybody. Mr. Hennon here. I'm going to continue where I left off on this particular problem and make sure that you are all there. So the last thing I had left you with is the fact that you could find time using this lovely equation over here if you had an initial velocity that was equal to 0 in the y direction. So something that's just moving horizontally, which is all of our projectiles right now. And this equation, when I calculated everything out, gives me that it's going to take 14.6385 or about 6 seconds to fall this particular distance. Great way to solve for, and it's a huge number that you can use, something important. So how far horizontally does the package travel? Well, horizontally, you don't really know a whole lot. We know the initial horizontal velocity, so this 115 meters per second. And we know it doesn't change because there is no acceleration in the horizontal direction. So the final is also 115 meters per second. We can use the time we just came up with, this 14.6 seconds, and we have to. We don't have anything else to find this information over here, because if I have that, then it's not going to allow me to actually find it. Sorry, I went forward, I didn't mean to. So our only equation is the fact that displacement in the horizontal direction is horizontal velocity. I'll just call it Vx because these are the same. We don't need a Vix or a Vfx. We can just call it Vx multiplied by time. So I'll just take this 115 meters per second, multiply it by the 14.6 seconds. And this will tell me how far horizontally. So basically from where the package would have, where they started dropping the package right here, all the way to where the package hits the ground. That's what we're finding, this X. That's the horizontal that we're talking about. We're talking about that, how far horizontally it traveled. And take out my handy dandy calculator. I still have that time saved in there. So I'm going to go ahead and use the full time, multiply it by 115. And I get 1683. If I keep it to 3 sig figs, just to kind of practice that, that'd be 1680 meters. So 1,680 meters is how far horizontally this thing is going to travel. Continuing with that, here's probably the hardest one, is finding the velocity of the care package right before it hits the ground, because common mistakes that happen here. I love this picture because it kind of breaks it down into two parts. One, if you were just to look at the package falling straight down, this A situation, it would go from here to here to here to here. It's basically accelerating in the vertical direction. Horizontally, thing that's kind of nice in B, you can see that this is going to stay constant. So you're always going to have this 115 meters per second, 115 meters per second, 115 meters per second. So horizontally, that doesn't change. What's happening, though, is it's gaining that little bit of vertical velocity. I don't actually want just Vy. I want the combination of both of them. So we have to kind of watch out for that. But our first step is let's figure out this. We want to figure out Vfy. What is this number? So I'm going to put in all the information I know. This is negative 1,050 meters. That's how far it fell. We know the acceleration of gravity is 9.8 meters per second squared. That's our acceleration, just the magnitude of it. Our initial vertical velocity is 0. We're not using the 115. That's x. So don't use that. And if I want to continue to use my time, this is my 14.6 seconds. Now, I like to do this using this information because this was all the information given to me in the problem, as opposed to using that time. So if I was trying to solve this, go back for just a second. If I was trying to solve it, I would use this equation. I would use the fact that Vf in the y direction squared equals Vi in the y direction squared minus 2 times g times y. However, since you do have time, if you want to use that, you could also use this equation, that Vf in the y direction equals Vi in the y direction minus g times t. Either one of those would work. They should give us the same answer. So I want to kind of show Viy is 0, so this part's going to disappear. So really what I'm doing for this Vfy, So I'm going to put in -2. It's going to be multiplied by 9.8. And that's going to be multiplied by my y, which was -1,050 meters. Negative because it's going downward. I plug that in on my calculator. So 1050 times 9.8 times 2, that gives me 20,580. Remember, that's VF squared. So now I need to square root that answer. And I get 143.457. So VFY equals 143. I'm going to go ahead and write a couple more digits just for a certain sake. You'll see in a moment why. Now, when I take a square root, remember, technically there are two answers. There is the positive answer and there's the negative answer. Remember, the square root of 9 is not 3. It's 3 or -3. Because if I take -3 times itself, I will get +9. If I take +3 times itself, I'll get +9. You don't see that with this equation. That's the only bad part of this equation. You saw this on the last quiz. You see it with this equation. So the advantage over here, you were trying to solve this one, VI is still 0. Then you get your -9.8 times this 14.6. So this one will actually show you that negative on there, which is kind of nice. I'm going to use the full answer, the full time. I never want to use a rounded time or a rounded answer. Always use the full one if you can. I get the exact same answer, except that I do have that negative on there. 4,5,7,3,1 meters per second. Now, technically, this would also be negative. Why do I know it's negative? Technically, it's the positive or the negative version, but I know this package is moving downward. I can see it in my picture here, so this should be negative. This is the common mistake. People stop there and they're like, I'm done. Mr. Hannon, there's my answer. That is just how fast this is going in the vertical direction. Remember, when I had my little airplane with my little airplane pin, and it's moving along and it drops this little care package, that care package is still moving forward. So they're both moving at 115 meters per second forward. It just gains some vertical velocity. So here is the fun. Guess what? We actually want not just VFY, we actually want that diagonal right here. This is what I actually want to solve for, VF. This is my VFY. This is technically my VFX. So I want the VF. I want that diagonal. How do I do that? Well, this side would also be VFY. Or this side would be VFX. So that gives me two sides of my right triangle. I just have to find the hypotenuse. I think it's easier to use this top one, and you'll see in a moment why I like to use that one. But to find VF, I have to use the Pythagorean theorem. So it's going to be my VFX squared plus my VFY squared. And so when I plug this in, I'm going to be putting in 115 meters per second squared, and I'm going to have that 143.45 whatever. Yep. 573 ... Now technically this one's negative, but we're going to be squaring it, so we won't actually see that. And usually when you're giving diagonals, you don't give those as negative. You can give negative when you've got just up and down, positive up, negative down, or you can give positive, negative if you're just talking about left and right, where maybe one way is positive and the other way is negative, however you want to kind of do it. But when you're doing the diagonals, we don't tend to do that. So this is just, we're just going to leave this as a positive answer. We want the magnitude of this velocity, and that's basically what we've got here. So I've already got this saved on here. I'm going to go ahead and solve for it. It's an incredibly huge number when you've got VF squared. It's this 33,804.99999. And then when I actually square root it, that should give me VF. That answer, and I get 183.86, blah, blah, blah. So I'm going to round this to 3 sig figs, so 184 meters per second. This is how fast the package is going, because as that package is being dropped, it's moving horizontally at 115 meters per second, but now it's vertically at 143 meters per second. So the combination of those two is this package, if you watch it, it's going to do this kind of diagonal. It's going to do a nice little parabola motion that we have. The other thing I would argue is you technically, if you want the final velocity, you also want the angle. You want the angle of declination. I want to know what angle it's going to land at. So that's this theta right here. And for theta, I think the best is to actually use tangent, because you know the opposite side is your VFY, your adjacent side is the VFX. So if you take the inverse tangent of your VFY over your VFX, that should solve it for you. So the inverse tangent of that negative, I'm going to actually leave the negative on there, and you'll see in a moment why I'm going to do that. Over this 115, and that, plug that into my calculator. I've got to make sure my calculator is in degree mode, otherwise we're not going to get the right number here, but I am, so I'm good. So I'm going to take the inverse tangent of that 143, actually negative 143 over the 115. And sure enough, if you put in that negative, what you will notice is that it'll actually give you the negative angle. And all that's doing is indicating that's an angle of declination, an angle that it's going into. So I would actually leave it with that negative. This would be negative, it looks like I got 51.3 degrees. So that's 51.3 degrees below the horizontal. We don't need a north, south, east, and west on this because we're just talking about a projectile launching and landing at this diagonal, and that's all we need. This has been horizontal projectile motion with Mr. Hennon at the Henstitute. I hope you have enjoyed. I broke it up into 2 parts to make each one a little bit smaller. And our lab is going to be dealing with that. Take care.